I kept saying there was only one video. I don't know why I was doing that. I just realized I kept saying, oh, there's only one video today. Only one video today. Well, there isn't. There's this video as well. In 6.5, the lesson before this, when we talked about the graphs of tangent, cotangent, secant, and cosecant, there was only one video about that. And we talked about that. But now we have another video here, so bonus video. Make sure we're watching this one again today on Friday, March 6th. And we're going to look at advanced trigonometric graphs. If you look at the homework sheet, if you look at the calendar, you can see that we're supposed to do 6.5 and 6.6 today. And this one, 6.6, you'll notice the homework, it says in-class activity. So there's no homework from this. It's just all an in-class activity. And the in-class activity is we're going to do a bunch of stuff on the calculator. So go ahead and take out your calculators. And I want you to kind of play along on the calculators. Try not to fall behind. It's easy to get lost. If you do get lost during the video today, then go home, watch the video again, and pause the video to make sure that you're entering all the things that you need to enter and kind of playing along and looking at all of these different graphs. If we were taking an analytical class, advanced calculus, Calc 4, Calc 5, and analytical geometry, this would be a much more important topic than it is today. Today I just want to look at some weird graphs and a whole bunch of different weird stuff and just kind of mess around with things and look at it and talk about their characteristics. So like I said, most of this will be on the calculator. All right, here we go. So first, bring out our calculators, turn on the calculators, and I want to look at a whole bunch of different graphs. For example, the first one I want to look at is f of x equals the sine of 2x. Now I already know what that looks like. The 2 here, what does that do? If I just stopped right here, what happened here? Has it been moved up and down, left and right? Has it been stretched? What's going on? The period has changed. 2 pi over b, 2 pi over 2, the period would be pi. So from 0 to 2 pi, instead of being one long between 0 and 2 pi, there would be 2 of them. But I'm not done, because this is going to be the f of x equals the sine of 2x plus the cosine of 3x. And we know what sine of 2x looks like by itself, and the cosine of 3x, we know what that looks like by itself. But when we add them, we have a little point of reference. What's going on here? And one of the things that I want to point out as we do these is I want to look at the characteristics here, and I want to look at the periodic nature. In other words, the fact that all of these are periodic functions and that they're going to repeat. The patterns will repeat, but they're not going to be such nice and well-behaved patterns as before. All right, so on my calculator, I'm going to go to y equals. I'm going to put in the sine of 2x, close parentheses, plus the cosine of 3x, close parentheses. I'm going to go to zoom to my trig and graph the function and look at the function here. Now, I wish I could zoom in on this. I wish I could take a closer look at this, because it's very important to see that we are getting a repeating pattern. Between 0 and 2 pi, this pattern repeats. I think it's a little bit more obvious if I change the window and my x's max and minimums, instead of using what they're doing, I'm going to go from negative 2 pi. Now, I'm plugging in negative 2 pi here. As soon as I do, it's going to change it into a decimal, to positive 2 pi. And again, as soon as I hit this, it's going to change it to a decimal. And then if I graph it, now I'm going from negative 2 pi to 2 pi, and I think we can see the pattern repeating a lot easier. The period of this function is 2 pi. The pattern repeats from here to here and here to here. This is the same thing as that. And then if I did another 2 pi, another 2 pi, another 2 pi, it would repeat. But notice how strange this thing looks. The sine of 2x and the cosine of 2x. So very, very strange types of things going on here in these different functions. All right, let's take a look at another one. How about if we have f of x equals the sine cubed of x? How would we graph that? Now sine cubed or sine squared, how would we graph that? In our calculator, what we're going to do in y1 is we're going to put in the sine of x with parentheses around it, cubed. Now be careful, this is not the sine of x cubed, this is the sine of x cubed. So in my y equals, clear out the stuff that's in there, open parentheses, the sine of x, close parentheses, so the sine of x. Now I'm going to close parentheses again to the third power. So I've got the sine of x cubed. Now I'm still going from negative 2 pi to positive 2 pi. I want to leave that alone. And I'm going to hit graph. It's still in my trig function. And as I take a look at it, again, we can see that it is a periodic function. It repeats every 2 pi. This strange bit over here and that strange bit over there, the pattern repeats. It's kind of hard to have a reference for, well, what does that look like? And we can't even think about these things. How about something like this? We know what f of x equals the tangent of x looks like. I don't know if we actually graphed that on our calculators yet. So let's go to y equals, clear out the stuff that's in there, and I'm just going to put in the tangent of x, close parentheses, and graph it. And there it is. I know we did this by hand. And we can see the asymptotes in there from negative 2 pi to positive 2 pi. That's regular plain old tangent of x. But what would this one look like? What if I did the absolute value of the tangent of x? What do you suppose this absolute value would do? Now think about it for a moment before we actually graph it. Okay, so what do you think the absolute value is going to do to this function? All right, so I'm going to go to y equals. I'm going to clear that. I'm going to go to my math, go over to my absolute value, and I'm going to put the tangent of x in there. So the absolute value of the tangent of x. If you've got one of the older calculators that says ABS and opens parentheses, plug in tangent of x and then close to make sure we've got the absolute value of the tangent of x, and then graph it and take a look at it. Now, can you see what happened here? The tangent of x had negative parts to it, but because we're doing the absolute value, all of those are reflected up. So we're only getting, everything is reflected up, the absolute value of the tangent of x, which is kind of a little bit more interesting here. All right, let's take a look at another function, and this one, I want to spend a little bit more time with this one. How about if we have the function f of x equals 0.5x plus the sine of x. And again, I want to focus in on this one from negative 2 pi to 2 pi. I think we've already got our window set up for that. So I'm going to go to my y equals, clear it out, 0.5x plus the sine of x. Again, we know what that line looks like. We know what that graph looks like. When we combine them, what on earth is going to happen here? It's very difficult. We really don't have any point of reference for this. We really don't know what this thing's going to look like. We're really not sure what to expect. So let's go ahead and hit graph and take a look at what's going on here. Now notice here, I don't seem to have a nice, well-behaved periodic function. This changes that. This is not the same side as happening over there. but I can kind of see the elements of sine, maximums and minimums, going up and going down. But it seems to be at a curve. Now, the interesting point here is, the application to this oscillation is, I want to take a closer look at this whole 0.5x. And what I'd like to do in y2, I want to graph 0.5x, and in y3, negative 0.5. Oh, no, that's not right. That's not right. That's not what I want. I want to do on either side of this. I want to do y2, I want it to be 0.5x plus 1 and 0.5x minus 1. All right, so let's go to our y equals. Down here in y2, I want to put in 0.5x plus 1. And in y3, I want to put 0.5x minus 1. 0.5x minus 1. And I want to graph. Those are both lines, right? They have slopes of 1/2, y-intercepts of 1 and negative 1. And I want to graph those two lines. And of course, what do you notice here? These are the bounds, aren't they? It's going up and down, that this curve is oscillating between those two lines, my maximum and my minimum lines. Just like when we had regular plain old sine, and we had the line 1 and negative 1, and sine oscillated between the two of them. Now, this is kind of at an angle here, and these two lines form the basis of this angle. There's a lot of applications to this. There's a lot of different things we can to do. For example, let's take a look at one more, a little bit more complicated oscillation. I want to take a look at a formula. Y1 equals 0.22 e to the power of negative 0.065x times the cosine of 2.4x. I want to take a look at this very strange graph right here. I want to take a close look at this graph. So I'm going to go to my y equals. Let's clear out all the junk that's in there. And 0.22 e to the power of negative 0.065x times the cosine of 2.4x. All right, so 0.22 e to the negative 0.065x cos times the cosine. So kind of putting it all together here. Take a look at it on the calculator. And for this one, I want to change the viewing window. Don't hit graph yet. I want to change the window. So for my window, I want to use the following window. Go to my window. My x minimum and my x maximum. Let's see, we're doing 0.22 here. So my x's, let's go from 0 to 25 scaled in 1 unit increments. My y minimum and my y maximum, 0.22 here. So I'm going to do negative 0.25, and my y max is a positive 0.25, and we'll scale it in 0.1 increments. All right, so my x minimum, 0. My x maximum, 25, scaled in 1 unit increments. My y minimum is negative 0.25, negative 0.25. My y maximum is positive 0.25 and scaled in 0.1 increments. And then go ahead and graph this function. Now remember when we did the bouncing spring, this would be a much more realistic equation for a bouncing spring, because if I start really high, it goes very low and then it goes up, but it doesn't go up as quite as high as before, and then it comes down but doesn't go quite as low as before, and then going back up and down and up and down, and you can see that the x-axis here would be the equilibrium point. At some point it's wobbling around, blah, 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 getting closer and closer and closer to that point. But the interesting thing here is I have boundaries up here and down here. So I want to graph two more lines. In y2, I want us to graph the line negative 0.22 e to the negative 0.065x, and in y3 I want to graph positive 0.22 e to the negative 0.065x. And you can, and maybe you can already see that these are going to be, we know that this is an e function, that this is exponential decay, exponential or growth here. So in my y's, in y2, negative 0.22, and then e to the power of negative 0.065x, and positive 0.22 times e to the power of negative 0.065x. So I've got the two boundaries without the cosine of 2.4x in there, and then graph those on top. And we can see that we've got a curve that represents the minimum values and a curve that represents the maximum values. And there's a lot of really cool stuff you can do with these videos. With all the different trig functions and the oscillations and what really happens, and data modeling. I haven't assigned any problems out of 6.6 and graphing them and looking at them. If you're into things like harmonics, especially music, is done this way, or any sort of periodic growth, economic, an oscillating spring, all that kind of stuff. It's all in here, and you can look through the chapter 6.6, look at some ideas, and play around with the calculator, see what happens. There's some really cool graphs and a lot of fun. I'm really hoping today, Friday, this is the last video lesson that I ever have to do. I'm hoping to be back on Monday. Right now I have no idea. It's all in the future for me. It all depends on how things went and what's going to happen next. And I was kind of hoping to be back this week, and that obviously didn't happen. So I'm really hoping to be back the week before spring break. And if not that, if things are not going very well and I need that week off and spring break, I'll definitely be back the week after spring break. I'm definitely going to be back after that. But I'm hoping that this will be the last video lesson that I ever have to do. I haven't really enjoyed these, to be honest with you. I don't like the not having feedback and talking and watching and seeing and kind of adjusting things as we go along. This is not the way I like to teach. So I really hope to be back in the classroom soon. I hope to see you guys. I don't know at this point if we've already Skyped and talked or not. I really don't know, but I'm hoping to be back very soon. And I'll see you guys soon. Have a nice weekend.